morning, everybody. I hope all is good with you. So in this module, we have covered a number of combinational circuits, starting from the code converters, at which we have shown that we can convert directly from binary to BCD and from binary to XS3. And then when it comes to the binary additions, we have shown that we can perform binary additions for one bit using two types of combinational circuits. The first type is the half adder, and the half adder is capable to add two bits at any given time, okay, and will produce a sum and a carry out. And if we would like to address a 3-bit additions, we need to use something called the full adder. So the full adder will be capable to add A, B, as well as like a carry in or Cn, okay? And will produce a sum and a carry out, okay? So the main difference between a half adder and a full adder is the full adder will be able to do a 1-bit addition between A, B, and let's say C, okay? Whereas the half adder will be able just to do A plus B, okay? And we have shown that like the full adder can be implemented using a half adder, like two half adders, okay, as indicated in this figure, okay? Okay guys, let's recall how did we implement the circuit shown here, okay? So we have, let's consider 1-bit addition. So we have 3 inputs, A, B, and C, okay? So that is 0, 1, 0, 1, 0, 1, 0, and 1, 1, 2, 3, 4, and this is 0, 0, 1, and 1, and this is 0 and 0, and this is 1 and 1, and those we will have 0, 0, 0, 0, and 4 ones, okay? And we will have two outputs. It's the sum, okay, and the carry out. It's worth noting that the subscript here is to indicate at which bit you are doing your arithmetic addition, okay? So in order to get the sum, like the sum of those 3 bits, it will be equal to 0 and the carry out will equal to 0. And the sum here will equal to 1, the carry out will equal to 0. And for this case, it's again 1 and 0. For this case, it's going to be like the sum 0, the carry out will be 1. For this case, it's going to be 1 and 0, okay, and this one will be 0 and 1, and for this one it will be like yes, this will be like 0 and 1 again, and for the final case here it's gonna be like 1 and 1. So we should write S in terms of the midterm. So what we have to do is, guys, okay, what we have to do, the sum we will look at here, we'll look at here, and we'll look at here, and we will look at here. So if you remember, the sum will be equal to, after the simplification, is going to be A XOR with B XOR with what? A XOR with B XOR with the carry, which is C, okay? So, and that is what's going here. The PI here, it's like, you know, the first XOR, and here it's another XOR, okay? When it comes to the carry out, okay, the carry out, we will look at here, and we'll look at here, we'll look at here, and we will look at here. So the carry out will be equal to, if we're gonna write it in terms of a sum of products notation, it's the sum of let's see here, it's gonna be at 3, and here it's gonna be at 5, 6, and 7. So 3, 5, 6, and 7. So let's write it in terms of min terms, okay? So at 3, to write it at 3, it's going to be A prime B C plus 5. It will be A B prime and C plus 6. It's going to be A B C prime plus 7. It will be equal the 7. It will be equal A B and C. So we can write it further by taking here, what we can do is we can take C as a common factor here, and this will be A prime B plus A B prime, plus we can take here AB as a common factor, so C prime plus C. So this will give me 1, and this can be further written in terms of three-level implementation as A, because this is exclusive OR with B, okay, and ANDed with C plus an AND between A and B, okay, and that's how we implemented the carry out for a 1-bit full adder. Okay, guys, now what we have to do is, let's suppose that we created a block diagram out of this circuit here, and it has A and it has B and it has a carry in, okay, and then we will have a sum as an output and the carry out as another output. What we can do is we can replicate this block diagram n times, okay, we can replicate it n times to do an n-bit addition, okay. So this circuit here is capable of doing 1-bit binary additions. If we replicate it n times while tuning the connection for the carry out and the carry in, we will be able to do it n times. So let me show you how we're gonna do it on Quartz again, okay? So guys, let's assume that you have already created a file that to implement 1-bit full additions as indicated here. So what you can do after compiling this file, you can go to File and you can say, look at Create Simple File for Current File, okay? And then you can name it something like Full Adder 2020 here, okay? All right. And then if we created a new file, okay, here, block diagram schematic file, we can go to the Gates Simple tool here. You go to your projects, and that is your full adder 2020, okay? So you can replicate it 3 times to do a 3-bit binary additions, or 4 times to do 4-bit binary additions, and so on. But how we can do that? So I've already done it here for 4-bit. So what you have to do, guys, in order to calculate the sum for the second bit, you have to ripple the carry out from the previous, which is the first full adder, and you have to ripple it to this full adder, okay? So basically, in order to calculate S1, S1 will be equal to the sum of A1, B1, as well as carry in 1, which is basically the carry out 0, okay? And we can do the same for the S2. So to calculate S2 here, S2 will be the sum of A2, B2 plus the carry out of the previous adder, which is Cout1. Okay, guys? Now, if you would like to simulate this circuit, so let's go ahead here, set as top level entity and compile it, okay? All right, so let's go back to our circuit here and file, new. Let's go and create a simulation file, okay? University program, VWF, and right there. So edit, insert, node or bus, and no finder list. So we have 4 input to represent the agent, which is like the A operand, and 4-bit to represent the addend, which is B, the B operand, and we have the sum here to represent the results. So what we're gonna do is we're gonna take all of them here, and okay. So what we have to do, guys, remember, according to our design here, A3 is the most significant bit and A0 is the least significant bit for the agent, okay? And similarly for B, B3 is the most significant bit and B0 is the least significant bit. And why we did that? And how did I know that? Because as you can see, in order to do the first addition, we're gonna add just two bit, which is A0 and B0, and for the carry in here, it's gonna be the ground. It's 0 because there is no carry out when we do the first addition for the first digit, okay, for the first bit, okay, guys. As a matter of fact, this full adder can be replaced by just a half adder because we don't need as carry in to do the first operation. So let's get back to our simulation file here. So what I have to do is, if I'm gonna do the simulation the traditional way, it's gonna be a bothersome job for me, okay? So what I can do is I will utilize the grouping feature of Quartz, and I can select A0, shift A3, right click, grouping, and group, and here I will name it A, okay? And again for B0 and B3, grouping, group, and please pay attention that I choose the radix to be binary. So that is B, okay? And the other thing, those output pins to indicate the sum for each corresponding bit. So grouping, group, binary again, and this I'm gonna name it the sum. But 1 second, I told you like A0 here is gonna be the most significant bit, the least significant bit according to our design. But according to this grouping, A0 is the most significant bit. What should I do is to invert reverse that group. So right click, reverse group or bus bit order. That's it, perfect. And we'll do the same thing for B. And the same thing for the sum, okay? All right, so by doing this grouping, I will benefit a lot. So what I have to do is, instead of assigning the input for each bit at a given time, I can assign it as a word. A word is a group of bits, okay? And in my case here, I have 4 bits, okay? So to do so, what I have to do, first of all, I have to go to edit, and I have to, like, let's suppose I would like to verify my 4-bit addition with two two examples, okay? So I have to go first, set the in time to make it something till like 200 nanosecond here, and then I have to go edit, and then the grid size I'm gonna choose it 100 nanoseconds because I'm gonna just verify it with 2 operation, okay, guys? So that's it. So like what I can do now is like click on this and double click, then I can choose the numeric or named value. So let's suppose I want to add here 0011, which is a 3, and I want to add it with 2, okay? I want to add it with 2 here, 010010. And for this one, for the second operation, for the second example that I want to do is I want to add something to do like 8 1 0 0 0 with 5. Okay, 1 0 1 and there's a 0 here. Boom. Then after that, option Quartus 2 simulator. Thank you so much. And then I have to run it. Okay, let's save it. Test here. Okay, guys, look at that. So basically, we added 3 and 2 and we got 5. And we added 8 with 5 and we got 8 with 5, we got 13. So if you want to choose, like verify the results in when it comes to decimal, boom, that's it. We have here like 5 and we have here 13. Okay, guys. Now let's suppose you want to do more than 2 operation. I already prepared a waveform here, and as you can see, I created the grid size to be 40 nanoseconds. And what you can see here is we are doing like a sum between 3 and 2 at the first grid size, at the first grid, sorry, and between like 4 and 1 at the second grid, and 8 with 7 at the third grid, and so on. Okay, the most important one that I would like to show you is the last one. I'm adding 8 plus 8, and the answer should be equal to what? 8 plus 8 equal to 16. But because we have a limited number of full adders, we will get an invalid result, which will equal to 0. Why? Because the 16 is 1 and 5 zeros at the end. Okay, so that 1 and 5 zeros at the, 5 zeros at the end, we will our circuit will not be able to display it. Let's take a look. Let's consider it something similar to a calculator. So you have a calculator that can display the numbers up to 15 digits. If your operation will produce a number with 17 digits, you get out of range error, and that's what's called overflow. Okay, so let's see what will happen here now. That's it, guys. You see that we get 0 even though the answer is equal to 16. Okay, when we do the addition on on a paper, on our paper, we have unlimited spaces to do so. But when it comes to computer, just remember that the number of your full adders will determine the number of bits that you can produce as the output. Okay, guys, so what we can do to solve this issue, and this is called an overflow, and this is what I'm going to explain it shortly. Okay, what we can do is let's go back to our circuit here, and we can create a block diagram from this 4-bit parallel adder to do an 8-bit. Okay, guys, 8-bit additions. But before doing so, we have to make sure that we have an output for the last carry out, because I want to connect the last carry out to what? To our new 4-bit parallel adder. So let's go here and see like how, and this is basically what we have to do is we have to go right click, set as top level entity, and then boom, like we compile it. Okay, so after that, let's go file, new, create a new no, before that we have to go here and we have to go to file again, create update, create simple files for current file, okay? And what I'm gonna name it here is 4-bit adder with a sign, because the carry out here is basically the carry out for the last full adder will be equal to the sign when it comes to signed binary numbers. Okay, and then I go here, back, file, new, block diagram schematic file. Okay, and here if I go here to the gate symbol, and then what I have to do, look at this, guys. So I have here one block that will be capable to do 4-bit addition. If I replicate it another time, I will be able to do what? 8-bit addition. Another time, 12-bit addition. But the most important thing, guys, what you have to do all the time is you have to replicate the sign here. The sign will be, okay, yes. So this will not work. Why? Because we have to go back here. Okay, we have to go back and we have to change as well that one to not be connected to the ground. Okay, so we have to go here, insert input pin, and we name that input pin is equal to what? This input pin, we name it CN. CN. Okay, perfect. Okay, and since we did some modification, we have to save it again, compile it. Okay, perfect. Now file, create, okay, 2. And let's go back to where we created the block somewhere here. Okay, let's go where file, new, schematic, and now, yeah, you see, guys, here I have the CN. So basically, if I want to do like a 3-bit, what I have to do, in addition to my regular input, I have to do the following. So what I have to do, guys, the sign here, or the final carry out, I have to connect it to carry in, okay, all the time, and I have to label it like this, and the same thing here. Okay, perfect. You see that, guys? So in order to, for the second 4-bit parallel adder to work, we need to get the last carry out generated from the previous 4-bit full adder. And in order to, for this full adder, in order for this adder to work, we need to wait until the last carry out from the full adder number 1 here to be computed and sent to what? To this full adder. And remember, we are doing this operation in a huge scale. What we will get? We will get a huge delay and a huge latency. Why? Because for this full adder to function properly, we have to wait to get the result from this full adder and this full adder. Full 4-bit adders and this full 4-bit adders. And this is called propagation delay. And propagation delay is a major issue when it comes to digital systems. The way to solve that when it comes to the addition operation will be covered shortly. Okay, guys, in general, all logic gates take a non-zero time delay to respond to a change in the input. Okay, so in an example here, let's consider we have a simple inverter, okay, gates, okay, guys, and we have B as the output. So if A used to be 0 and it changed to 1, okay, that is A. B, guys, will be equal to 1, and that transition will not be reflected momentarily. Because, you know, like it's a material and there is some resistance, and the signal needs some time to travel. So basically, in nanoseconds, this output will be changing to then 0. So this time, guys, you know, getting the result at this time, this is a transition time, and will give me like false output. So what I have to do is to wait until the output change to a steady state, okay, steady state, then capture my output. So in any combination circuit, the signal must propagate. The signal must propagate uh, through the gates before the correct output is available at the terminal. So the total propagation time is equal to the propagation delay of a typical gates times the number of gates level in the circuit. When it comes, why we're introducing this, okay, and let me show you here in more details. Why we're introducing this? Because the propagation time is very important when it comes to parallel adder. Remember, guys, here S2 will not be computed until I have the carry out from the previous adder, which is like, you know, C out 1. And C out 1 and C out 1 will not be computed until I have finished what? The arithmetic operation at the previous adder. So basically, guys, this propagation delays is rippled based on like linearly based on the number of full adders that I have. So let's assume that this full adder, any full adder, okay, implemented using a NAND only solution, will produce 30 nanoseconds to give you the output at the terminal. So basically, in order for me to calculate the sum and the carry out for adder number 2 here, I have to what? Multiply the basic propagation delay, which is 30 nanosecond, with the 3, and the time for this 3-bit parallel adder to produce the sum will be equal to 90 nanosecond. I know it's not a lot, but imagine you have a million of full adders blocks here. So what you're gonna do? Like, you're gonna have a big huge delay, and the delay is very critical when it comes to the, like, you know, digital circuits. Let me give you an example from real life. Imagine you're playing first person shooter game, and you have a delay of 200 milliseconds. So your opponent will be able to kill you even before you're aiming to it. And that delay, that latency, that input lag, it's called, will depends on the circuit that producing that output. Like in your in our like analogy here, it depends on the lag, the input lag of the TV plus the network input lag. Okay, guys. So basically, now if I have a 64-bit adder and all of them are using the 30 nanosecond full adders, what will be the final propagation delay for that adder? is gonna be 64 multiplied by 30 nanosecond, and it's gonna be 192 millisecond. As I mentioned, this accumulated delay in large parallel adders will be a cumbersome issue. So what's the solution? The solution is either to, like to build your adder using a very fast and effective gates, like for instance, like if it's built through TTL, change it to like CMOS because it's more like faster, or we can use something called a carry ahead logic circuit. Okay, carry lock ahead circuit. So what is the main goal of that carry lock ahead logic circuit? It will generate the carry input signals directly from the inputs rather than waiting for them to be calculated and rippling it to the correspondent adder. So let me show you in details here. So basically, guys, you remember that is like, like if we forget about this block diagram, okay, guys, this is a typical 3-bit adders, okay? But instead of rippling the carry out from the first adder to the second adder, what we are doing here, we are calculating the carry out in advance. So how to do so? Now, what is the carry in 0? The carry in 0, if we have any like operation here, like, let's suppose that we have a 3-bit, so we have A2, A2, A1, and A0, and we have B2, B1, and B0, okay? And remember, like we're doing like 3-bit addition, so basically the carry in here, we will have a carry in here. So if we're just adding these two numbers, this carry in will be equal to 0. So the carry in 0 will be equal, which equal to Cn here. That is Cn because it's directly connected, as you can see, guys. It's directly connected. Okay. And for the carry in out, how we can get the carry in Cn out here? So the Cn out here, as you can see, Cn out is connected to C out 0. So C out 0, how we can calculate C out 0? Remember, guys, the full adder circuit here, okay? So the carry out 0 will be equal to this expression. So it's gonna be the previous carry, which is Cn, okay, plus, yes, plus what, guys? Plus what we calculated here, which is, that is the, like, the A0, B0, those are OR, and A0, B0 added together, okay, guys? Okay, because, yeah, okay, guys? So basically the carry in, and that's basically the equation you can get from the, from the carry out for the half adder, okay, guys? So the carry in 1 here is no longer depending on the carry out 0. Now it's depending on the carry in, which is basically one of the input that we have. That is the carry in, okay, guys? The carry in here, okay? And A0 and B0, we know it because, guys, they are the inputs, okay? Now, when it comes to the Cn, that's for Cn2, Cn2 will be equal to Cout2, and Cout2 can be calculated by what? By applying the equation for the carry out directly for the full adder. And how did we calculate Cn1 here? We calculated Cn1 as Cn A0 or B0 plus the AND between A0 and B0. Okay, that is what? That is, guys, for Cn1. But Cn1, we already calculated it in terms of the input, okay? Which is, we can replace this Cn1 here, and then we're gonna get this expression. So as a matter of fact, in order to calculate the sum 2, we will not wait for the Cn2 to be computed, okay? So Cn2, Cn1, and Cn0 will be propagated through the logic gates directly and at the same time of the other carries. So Cn2 will be propagated at the same time like Cn1 and at the same time like Cn0. Okay, guys? So this gain speed of operation, but at the same time, like what we did, we have to implement those, those operation using logic gates and replace it in this block diagram here. So basically, we're increasing the complexity of our 3-bit parallel adder in order to what? Or at the at the expense of at the expense of producing a very effective and fast output. Okay, guys? So again, just to be crystal clear, instead of rippling the output, the carry out from each adder to the second adder, what we have to do is we have to find an equation. That equation will calculate the carry out in terms of, or as a variable of the inputs that we have. So we know that the inputs we have Cn, A0, B0, A1, B1, A2, and B2. Okay, guys? So how to calculate the carry in 0? The carry in 0 is basically carry in, because when we did our addition here for the first A0 and B0, so basically it is Cn0 and Cn0 in our case it's equal to 0. So that is Cn0. In order to calculate Cout, what is Cout here? Okay, Cout, if we're gonna write it in terms of Cout0, if we're gonna write it in terms of the output of the full adder, that is its equation. Okay, guys. Now, in order to calculate, Cout, Cout here, that Cout, in order to calculate that Cout, we need the A1, B1, and Cn1. So instead of waiting to calculate Cn1 from this adder, what we're gonna do is, find a way to calculate Cn in terms of the input. So what Cn1 is equal to Cout 0. Cout 0, we already calculated here. So that's why we are capable to get what, to find the S1 as well as Cout 1 momentarily. Now, for Cn2 here, Cn2, it's basically, well, it will be used Cn2, Cn2 will be used with A2 and B2 to calculate the sum 2 as well as Cout 2. Okay, but how to calculate Cn2? Cn2 can be calculated because basically we know that Cn2 is basically the Cout 1. Okay, Cn2 is basically Cout 1. So Cout 1, we already calculated that equation. And similarly, Cout 1. And similarly, instead of representing it in terms of Cn1 here, we can substitute the value of Cn1 directly to here, and that's why we get this expression. Okay, guys? So basically, the carry logic ahead circuit will increase the speed of the arithmetic addition at the cost of increasing the complexity of your hardware or of your gates. Okay, guys? All right. Now, how we can perform binary subtraction knowing that we have already designed the parallel adder. Okay, so if you remember, guys, like in order to do A minus B, and we don't know how many bit is in A and how many bit in B, but basically we can rewrite this as A plus the 2's complement of B. Okay, in order to calculate the 2's complement of B, it's basically the 1's complement what of B plus 1. Okay, so how to get the 1's complement? Remember the shortcut, guys? We can flip or invert the bits of B. Okay, guys, and that's why the 1's complement is important. This is the answer for the student who asked why we study the 1's complement. Okay, guys, so if we go back to quarters here, okay, so what we can do in order to change this 4-bit adder into like a 4-bit subtractor. So what we can do is simply delete this connection, delete this connection, delete this, no, delete this connection, and delete this connection. And instead of that, instead of connecting B directly, what we can do, we have to invert B. Okay, so we're gonna invert B at each bit. So that's it. We go here and we go to primitives and not. Okay, thank you. Okay, 1, and then I have here 2, and I have here 3. Okay, and basically I have here something I did not delete it. So Control C, Control V, boom. Okay, and for this one, just to make sure that this thing is not in my face. Awesome. Okay, guys. So, okay, now this one is not connected yet, so I'm gonna connect it. That's it. But remember, guys, in order to do the, in order for me to be able to do the subtraction, and I have here A2, A3, sorry, A2, A1, and A0. So what I have to, what I did here, I inverted all of these. So here I'm gonna have B3 prime, and I have here B2 prime, and I have here B1 prime, and I have here B0 prime. Okay, and then I will do like a simple addition using my full adders. But the answer is not correct because I have to add 1. So in order for this one to work, that's just a 1's complement. This is just a 1's complement. So I have to use 1 here. Okay. So how I can use 1 here? I will simply go back here and change this from ground. Okay. And then go here and attach a VCC. So as you can see, guys, this circuit now is a binary subtractor. And basically you can go ahead and simulate it the same way that I've shown you how to simulate the parallel 4-bit adders, and you will get a subtraction operation in instead of the addition. Okay, but this design, guys, this design is expensive because basically we changed the whole full adder into a full subtractor. So can we use the same hardware we did to do both addition and subtraction? The answer is basic. So if you remember, guys, when we do the addition, the carry in was equal to 0, and that's why we use the full adder for the first to perform the first addition operation. And when we did the subtraction, the carry in is equal to 1. Now, inverting the other operand, which is in my case B, what I will do is XOR the B with the carry in. So if I have B0 and I XORed it with 0, if you remember that from module 2, guys, this will give you B0. And if I have B0 and the carry in was equal to 1, that means I'm gonna get the inverted version of B0. Okay? And that's exactly what's going on here, guys. So what we're doing here, in order for us to subtract 0010, to do the subtraction between 0010 and 001001, so what will happen is basically this 1 B will be XORed with 1. So 1 XORed with 1 will give you 0. 0 XORed with 0, like XORed with 1 will give you 1, and 0 XORed with 1 will give you 1, and 0 XORed with 1 will give you 1. So basically it's like an inversion because we are doing this. Okay, guys? So what will happen then? Then this will become like a direct addition between 0010 as well as 1110. Okay? So when we do that addition, we will get what? Let's do it here. Okay, let's do it. So basically we have 0 0, sorry, 0 0 1 0, 0 0 1 0, and 1 1 1 0. So let's do the addition, the like direct addition between them. 0 0 1 0 1 and 0, and we have a carry out of 1. Okay, and remember what we're gonna do is we have a carry in. You remember that the carry in, so I forget that carry in, so this will become 1. Okay, and we're gonna ignore the carry out, so the answer will be 0 0 0 and 1. Okay, so what we did, guys, we added A to the ones complement of B plus 1, and that is equal to A minus B. Okay, guys? So the bit E here will determine if this circuit will work as a direct addition or as a direct subtraction. Let's get to a terms what's called an overflow. Okay, guys? So the overflow is an important issue for computers because when it comes to us as a human, we can do the addition and the subtraction with unlimited number of digits. Okay. However, in computers, you have noticed that in order to implement like a 3-bit parallel adder, we need 3-bit full adders. Okay. Okay, guys. So basically, storage in computers is limited, similar to calculators. The calculators, if it can run maximum of 15 digits, if you're gonna get an output of 20 digits, you're gonna get an out of range error, and you try that. So in general, overflow, guys, happened when we're adding a number, that are what that are like both positive or both negatives. They have the same size, the same signs all the time. Why? Because when we add like a positive to negative, for sure the result will be less than any one of them. Okay, or less than one of them for sure. Okay, so let's take a look on some example and refresh our mind about an overflow condition. So basically here, if we added, this is what, guys? This is, as you can see, that is, that is -2 added to 4, because this is in the 2's complement. Remember that is in the 2's complement. -2 plus 4, the answer will be what? Will be 2, and we will not have an overflow. Okay. So how it's happening? It's 0, 0, and 1 plus 0. This is 0, 1, and then we have here 0 and 1, 0 and 1, and here we're gonna get what? Like we're gonna ignore the carry. That's why we get what? The 0 as a sign bit, and this is 2. Okay, guys? However, look at this example when we gonna add what? When we gonna add, put two positive numbers here. Look at this. So we have 3 as positive and 6 as positive, and we added them together. And once we added them together, that's will give you 1, 0, 1. So 0, and this one, this is what? This is 9. And since we have the most significant bit as a sign, that is -7. Okay, that is not 9, because you remember, guys, we have a limited 3-bit, you know, full adder, and the most significant bit here will represent the sign. So basically what we got here is 1001, and 1001, if it's not like if it's an unsigned number, we know that is 9, that is 9, and we have no problem with that, and this is, as a matter of fact, this will be correct, 9. But here, that is negative. In order to get the magnitude, we're gonna take the 2's complement, so we keep this one and we invert the others. So that is -7. Okay, that is -7. Okay, so that is an overflow. Okay, so overflow occur when two values of the same signs are added. Result won't fit in the number of the bit provided, and the result has the opposite sign. Okay, guys, that is the two conditions to detect an overflow. So how we can translate that in our favor? How we can detect, use a special hardware? We as a human, we know that. We know this is an overflow conditions, and we can adapt it by increasing the number of digits. Okay, by adding here 0, so this will become positive. Okay, but as a computer, how can you detect an overflow as happened? So basically, the way to do so is by XORing the carry that's coming to the last full adder, and the carry that is producing from the last full adder, or is by basically, as you can see, XORing the carry that's coming to the full adder that produces the sign, as well as the sign bit. Okay, so let's take a look in our example here. Like if we have here the carry out here, if we XOR 0 with, let's take a look here. We have here the operation is addition. That's why m is equal to 0 and the carry in is equal to 0. So we have 6 plus 6. So 6 plus 6 will give you what? Will give you 6 plus 6 will give you 12. Okay, and as you can see here, when we have, okay, let's do it 0 1 1 0 and 0 1 1 0. So that is 0, that is 0 and 1. Okay, and this is 1 and 1, and the answer is a 12. And this is, we get what? Oh my god, we get what? -4. It's a sign that is, that is not equal to positive 12. Okay, guys. So how we can detect that, guys? If the carry out, if the carry in XORed with the carry out for the last full adder will produce 1, that means an overflow is happening. And if it produces 0, that means an overflow is not happening. Okay, guys, let's take a look on our example in more details. So basically, we are doing the additions here, and as you can see, we are getting -4 instead of getting 12, because we're considering the most significant bit as a sign bit. Okay, guys. So how we can detect that we're getting a wrong output is, look at this. The last addition here, like you see that here we have 1 and 1 is 0, and we have 1. So the last one will give you what? Will give you a carry out of, of 1. And if we XOR it from the final carry out from this full adder, which is 0, 0 XOR with 1, remember it's an inequality, so this will produce 1. That indicates an overflow happened, okay? Okay, guys, let's take a look on a counter example at which we are subtracting 6 from 6. So the answer will be equal to 0. So how we can do that in our given implementation here? So basically, the E bit here will be equal to 1 to indicate that we are doing a subtraction in a subtraction, not addition. And basically, let's take a look at what is going on here. So when I add 0110 to 1010, the answer will be equal to 0. And if I take a look here, guys, look at here. If I take a look at the carry that is going to the most significant full adder and the carry that is producing from the most significant full adder, both of them are equal to 1. So one exclusive OR with 1 inequality will give you 0. That indicates no overflow happened, which is actually our case, because if we add plus 6 to minus 6, the answer will equal to 0, okay? Or if we subtracted 6 from 6, the answer should be equal to 0 and no overflow happens. So an overflow happened, just to vacuum everything. An overflow happens if you add two positive numbers and the answer will be equal to a negative number, okay? Or if you add two negative number and the answer is equal to a positive number. You can look at the overflow from a different direction, okay? Which is an overflow will happen if you have like a circuit that has 4 registers or 4-bit capable to produce an output with 4-bit, and your results equal to like 5-bit, okay? In this case, your answer is out of range and does not reflect the correct output, okay? So overflow is a big issue when it comes to computers and can be detected by XORing the carry that is going to the carry that is going to and from the sign bit. Okay, guys, take a break and I'm gonna see you shortly in another video.